Nick Fryer, and today we're talking about the Physics 2 Lab 2. So this lab is very similar to Lab 1. We still prepare charged pieces of clear tape. We observe the interactions between those pieces of tape and other objects, and we determine the excess charge on the tape and simulate these findings with a computational model. The real big difference is that we're not treating the tape as a rod of uniformly distributed charge, rather than a point charge like we did in Lab 1. These conclusions were similar, but not exactly the same as Lab 1. So a charged U-tape was found to have a net positive charge just as before, except this time it's a little bit different at 2.19 times 10 to the negative 8th coulombs. And a charged U-tape has a 1.37 times 10 to the 11th electron deficiency, with the ratio of deficient electrons to total atoms at 4.98 times 10 to the negative 7th. So fundamental principles, just as before, we have gravitation near the surface of the Earth. It's minus mg in the y-hat, just as before. We also have electric force and Coulomb's law, which is very similar, except this time we are also modeling the electric force as our charge times our external field, which will come in later. And just note that R is the vector that points from the source to the receiver of the force. This time we also have an electric field of a rod with uniformly distributed charge. Observation points are taken to be perpendicular to the lower U-tape. And the electric field formula takes into account the length of the tape, the total charge of the tape, and the distance from the tape to the observation point. And that formula can be seen here. Just note that this is an estimation because we only model each tape as some finite number of point charges. And while the actual number of point charges on the tape is technically finite, it's much higher than what we're modeling it as. In my case, 10 point charges or 20 or 30. So the procedure is very similar to Lab 1. We still make the two U-tapes. We place them close to each other. We observe their interactions. And we ultimately end up suspending one U-tape and holding the other U-tape below it until it makes the first one float. And then we measure the separation distance between the U-tapes, and then we do our data calculations. So assumptions very similar to before. We assume, again, that both tapes have equal charge since the U-tapes were all created using the same method. External gravitational interactions were ignored, and if air resistance did play a part, we would just ignore it anyway. Now, this time we also assume that charge is evenly distributed along the tapes and that we can model them as some small number of adjacent point charges rather than a single point charge as we did in Lab 1. So our observations are all from Lab 1, so the U-tapes repelled, but they were attracted to negatively charged objects, meaning that they were positively charged. And when we did the floating U-tape experiment, we had a separation distance of 1.8 centimeters. So this is a free body diagram. It's very similar to Lab 1, except this time we have kind of these bars across in the horizontal direction rather than circles as before, because they're no longer being modeled as point charges, but rather line charges. And just note again that these tapes are at equilibrium, so the electric forces are equal in magnitude and opposite in direction. So from the experiment in Lab 1, we found that the suspended U-tape had an area of 0.00275 squared meters. The number of atoms on the sticky side of tape was calculated using total area over the area of an atom. And separation distance between the two U-tapes, again, was 1.8 centimeters. And the total weight of the tape was about 0.002156 newtons. So the charge of the suspended U-tape, like I said, was calculated to be 2.19 times 10 to the negative 8th coulombs. This is using the formulas that we had before, as well as noting that in equilibrium, we have the electric force is equal to the negative of the gravitational force. We had a deficiency of 1.37 times 10 to the 11th electrons by just doing total charge over the charge of one proton. And we had a ratio of deficient electrons to total atoms of 4.98 times 10 to the negative 7th. So again, we used the formulas that I listed before. We ultimately rearranged the formulas to solve for our charge Q, and using our separation distance, we got 2.19 times 10 to the negative 8th coulombs. This is the computational model. Most of it was given to us, except we did have to input certain numbers and functions to make it work for our experiment specifically. And this is the rest of the computational model. And these are the results. So you can see the green electric field vectors pointing radially outwards, as well as the ultimate electric and gravitational force vectors. So as our discussion, again, we calculated the charge of the tapes and the number of deficient electrons, and some error sources include inaccurate measurements. The U-tapes, we assume that the U-tapes to have uniformly distributed charges, but we treat them as some small finite number of adjacent point charges, so it's a little bit inaccurate. Not holding the U-tape exactly parallel, and some rounding error. So as a discussion, if we modeled each of our tapes as a single point charge like in the previous lab, so we compare these two charges, and ultimately our charge was greater for the line charge model in Lab 2 by a factor of 2.48. And these estimates differ because Lab 1 treated the tapes as point charges, which is just not as accurate as Lab 2. Um, Lab 2 is still slightly inaccurate because we're not treating them fully as line charges in our computational model, but it is likely more accurate because tape really would have more than one particle. It's not just a point charge. So it's more shaped like a rod than just a single charge.